Our innovation is a novel wave energy converter which uses a winch-powered PTO and a flywheel system to generate and provide a renewable energy source from waves. In the wake of technological development, the imperative for meeting the ever-increasing energy demand without sending us into ecological overshoot becomes much more dire. Energy demand in Ontario is expected to increase to 75% by 2050. We wanted to find an innovative yet efficient way of meeting this demand. Currently, the only way for meeting this demand globally is through the use of fossil fuels, yet this expedites and exacerbates the effects of climate change.
Currently, one way we are shifting away from fossil fuels is through the use of renewable energy. Yet, even that only accounts for a fraction of global energy consumption. One new emerging technology is wave energy converters, or WECs for short, which use the mechanical motion of waves to generate electricity. After extensive research, we found some of the major issues with current WEC designs, which inhibited their feasibility in real world applications, and our innovation aimed to address these issues. The main overarching issue with current WECs is their high levelized cost of energy, or LCOE for short. There are two main things which impact LCOE. The first is manufacturing and maintenance costs, and the second is the amount of energy produced and how smoothly it is integrated into electrical grids.
There are a couple of things which impact manufacturing maintenance costs, but the main issue is their complexity. Current designs contain a multitude of moving parts, which when exposed to the rhythmic consistent force of waves, tends to break down over time. Furthermore, as seen in this animation of Core Power's wave bobber, all of the main electronics are housed within this floating buoy, making it vulnerable to storms and extreme weather events. As seen, their buoy runs along a fixed track with a fixed length. This means that if rogue waves or storms hit the WEC, the distance of the buoy bouncing up may exceed its track, causing extreme structural damage. As seen in their video, they trimmed the buoy so it stays still during storms, nullifying this opportunity for extreme energy capture. Our proposed solution to this is a winch-powered power takeoff system, or a PTO, inspired by cardholders. We found that such a small device was able to store large amounts of string within its spool, and we decided to implement this here. Now, when rogue waves or storms hit our WEC, the spool just releases more and more rope to accommodate. This also increases the durability and lowers the manufacturing cost of the system. Instead of investing the technology in making a strong gear-powered rail system, we can now invest into making a hyper-strong rope instead, bringing our LCOE down even further.
The second major problem we tried to tackle was to increase electrical output and to smoothen this output for grid integration. Electrical grids require stable voltage and predictable ramp rates for safety, but wave characteristics fluctuate often, and power increases exponentially in relation to wave height, so small changes lead to big power changes. To not destroy the grid, electrical generation must be smoothened out. And to achieve this, we decided to employ a flywheel, which stores rotational energy and smooths power output by dampening the sudden energy spikes that could overload electrical components while still spinning the generator during times of low wave energy. This helps increase electrical production due to the constant motion and levels out differences in energy for smoother integration into transmission and storage systems. In addition, the winch mechanism enables electricity to be generated when the buoy moves in any direction, enhancing electrical output.
We decided to first tackle the idea of a flywheel. We spent a week designing, CADing, and prototyping our first proof of concept. After many failed prints and multiple broken pieces, we came up with this design. Due to the fact that we are mainly testing the feasibility and potential of the flywheel, we decided to skip the waterproofing part and make this prototype screw into a platform. This would make testing much easier. As seen from this video, as the buoy basketball moves up and down, it spins this lever. Through this large gear ratio, it spins the flywheel really fast. This flywheel is, in turn, coupled with a clutch, allowing it to spin only in one direction. This means as more and more waves hit the system, it continues to maintain the flywheel's speed. We did some preliminary testing in the wave tank here, and as you can see, the flywheel continues to spin, even with such irregular and small waves.
In order to test our prototype, we needed to find a way to create and control waves in a tank. After some research on wave tanks, we constructed a platform that utilizes a bottom hinged flap wave maker design and also holds our onshore prototype. As seen in this video, we fabricated this flap from a chopping board to help move the water. When we add a breakwater such as a beach or shoreline near the end of the tank and motorize the flap, we will be able to create consistent, reproducible waves that allow us to change properties such as amplitude, period, etc. for testing by changing the speed at which the flap moves.
When designing our first prototype, we found a couple of issues which impact our design. The first was friction. Because we were using 3D printed parts, which are not inherently smooth, we found that when we tried to gear up the ratio to spin the flywheel faster, it would cause a lot of squeaking and end up slowing it down even more. One way which we could propose to solve this in a full-size model is to use lubrication. Another problem we ran into was the fact that 3D printed parts are not very strong. We found that when designing stronger parts, they required a lot more time to print, and this increased the time it took to reiterate.
We believe that our innovation will help coastal communities by providing a local, renewable energy source. This lowers the cost of energy for them, as well as providing them with a multitude of jobs. When coupled with offshore wind farms, it offers governments an easy, scalable energy source, which can aid the public in the shift away from fossil fuels. In terms of our next steps, our project is still in the early developmental stages. And without proper testing or simulation equipment and software, it'll be rather difficult to achieve accurate data and progress even further. However, these materials and softwares are expensive, which is why we believe that the prize money from Ingenious Plus could help us. Furthermore, before implementing, we want to further test and print a prototype, which includes the winch powered PTO system. We could also expand and improve this wave energy converter further by incorporating various ideas such as active PTO control or generator control to maximize electrical generation by syncing the buoy's motion with the waves to amplify its motion. With this prize money, we would be able to utilize more high end simulation software, buy more hardware for quicker and more refined prototyping, and enable us to test on larger scales, such as in pools. Thank you very much for listening.